Good Information Courses by Plastic Ingenuity. In this course, you will learn how thermoforms can play a critical role in a circular economy. The course will include an overview of the thermoforming process, types of polymers used in thermoforming. We'll talk about mechanical recycling, how advanced recycling can complement mechanical recycling, and finally, progress being made toward a more circular future for thermoforms. Let's start our thermoform circularity journey by reviewing the thermoforming process. So in this first lesson, we will discuss what thermoforming is, walk through each step of the process, discuss how thermoforming compares to other plastic processing technologies, and review the entire product lifecycle. Let's get started. Simply put, thermoforming is the process of heating a plastic material and shaping it using a mold. So let's take a look at some common types of thermoforms that you encounter every day in your life. Thermoforms provide many benefits to society, from preserving the food that we serve our families at night, to protecting the medical devices and pharmaceutical products that we trust to save lives. However, not enough thermoforms get recovered for recycling. We need solutions that keep thermoforms out of landfills, out of our environments, keep them in our economy so that we can continue to reap their many benefits. The thermoforming process begins with a roll of plastic sheet. That plastic sheet is made in an extrusion process. Let's talk more about the extrusion process before we dive deep into thermoforming, since extrusion is a critical input to thermoforming. The rollstock materials, namely resin and colorants, in the form of pellets or flake, are conveyed to and precisely blended in a hopper system. The blended formulation is then fed into the throat of the extrusion system. Inside the extruder barrel, the materials are heated to their melting point by heater bands and the friction caused by a large rotating screw. The rotation of the screw forces the molten plastic to exit the point of the extrusion system, known as the die. The die spreads the material out to a flat shape. The material exits the die to a series of rollers. The rollers cool the material and pull it through the system. The final thickness of the sheet is measured in line for instantaneous feedback. The scrap from the process, known as edge trim, is fed back into the blending process for reintroduction into the sheet. Thermoforming can happen in line with the extrusion process or offline, as shown in this schematic. Back to our video. The extruded rollstock is fed into the machine where it is heated to a pliable state in the oven. These oven temperature settings are specific to the type of plastic being processed. The sheet then enters an aluminum mold where it is formed to its designed shape by air, vacuum, and sometimes a mechanical assist called a plug. On the table here, we have some examples of thermoform mold components. This is a cavity plate with 4 cavities machined into it. You can see here, this is the female cavity that the sheet gets formed down into to form the shape of the part. And here we have the plugs. So this is a plug plate with 4 plugs. The plugs match up with the cavity and push the sheet down into the cavity to maximize the material distribution. The next step in the process is part trimming. Trimming can happen by 2 primary die cutting methods, known as steel rule or match metal. Steel rule knife dies are essentially industrial-sized cookie cutters. Thin but very strong bands of steel punch the desired shape of the part. Matched metal dies resemble industrial-sized paper hole punches. The trim is sheared when a male punch pushes it through a female die. This video shows how matched metal dies function at very high speeds. The trimmed parts exit the die in nested stacks. Custom automation is often utilized downstream of the thermoforming process to aid with the secondary packaging process. In this video, stacks of nested lids are sealed inside of a sleeve bag. The sleeves are conveyed to a manual packaging station where they are placed in corrugated cartons. The cartons were erected automatically at the point of packing. The packed cartons are then sealed with tape through a machine and stacked on pallets. One very important note before we move on. The plastic waste from the process, known as web scrap, is ground up into flake, where it is then conveyed back to the blending unit for reintroduction back into the part. So we aim for zero waste. At this point, you may be wondering how thermoforming compares to other plastic processing technologies like injection molding and blow molding. Now we're going to get to that, but before we do, there's one important distinction that we need to make. Thermoforming processes can be characterized as two types: thin gauge and thick gauge. The scope of this lesson is thin gauge thermoforming, since that's the predominant method used to make packaging. Thick gauge thermoforming often uses sheet greater than 1/8 of an inch thick to make durable goods. Some examples of durable goods made from thick gauge thermoforming includes truck bed liners and canoes. Back to packaging. Now it's no surprise that the use of plastic in packaging is ubiquitous, given its durability, lightweight nature, and low energy consumption. Plastic can be molded or shaped or extruded into a variety of shapes and sizes. So let's walk through some common examples of plastic packaging. Bottles are used to contain beverages and household products. They are typically made by a blow molding process, where air forces the plastic against the vertical walls of a split mold. Tubs are often injection molded and used for a variety of applications like chilled dairy products. Now we're going to talk a lot more about injection molding in the next section. Pouches are typically made by laminating together film structures. They are a very lightweight option to protect and preserve food, like this example, or healthcare products. Bags are made from a blown film process, which essentially blows a giant plastic bubble to stretch a film to its desired size. Finally, milk jugs are another example of a blow molded product used extensively to protect an essential product. Injection molding has the most overlap with thermoforming, since they're both used to make rigid, thin wall products. Now, let's take a deeper dive into injection molding. In an injection molding process, plastic is blended in an extruder similar to thermoforming. However, instead of extruding through a die, the plastic is injected by a nozzle directly into a mold, at very high speeds. Unlike thermoformed molds, injection molds have two halves, known as a cavity and a core. The plastic flows between the cavity and core void when the mold is closed to create the desired part. A high tonnage clamp keeps the mold closed while the parts cure using chilled water inside the molds. After initial curing, the molds open and the parts are ejected onto a conveyor or picked from the mold using automation. Injection molding is a very precise process since the part geometry is controlled from the inside and out. Also, scrap is very minimal. On the downside, tooling is very expensive and material formulations can be a little more limited. Also, wall thicknesses are higher to allow the plastic to fill the entire mold. All right, now that we've reviewed the common plastic processing technologies, let's talk a little bit more about the advantages of thermoforming. So thermoforms have immense utility across a wide variety of applications. Plastic can be thermoformed into a wide variety of shapes and sizes. The process enables very efficient material usage, which can result in lighter weight packaging. Also, material structures can be easily customized to meet the key performance requirement of a package. This includes preservation and durability. Thermoform tooling is inherently more flexible and cost-effective than competitive technologies like injection molding. Now, before we move on to the next lesson, let's review a typical life cycle of a thermoform. So after production at Plastic Ingenuity, thermoforms will go to the brand owner. The brand owner will fill the thermoform package with the product and assemble it with other packaging components like the lid film and labels. The completed product and package is then sent to a consumer or end user for product use. The consumer then disposes of the packaging materials after use. The disposed thermoforms either go to a landfill or are recycled, depending on many factors which we'll discuss later. However, in a circular economy, the recycled thermoforms will come back to PI for use in new packaging. Let's recap the thermoforming process before we move on. Thermoforming is a process that heats plastic material in the shape of a mold. The process input is plastic rollstock that is made in an extrusion process. The plastic rollstock is heated to a pliable shape where it is formed in a mold using air pressure, vacuum, and mechanical assist. The formed parts are then sent to a brand owner where they are filled with the product, assembled with other packaging components, and then sent to a consumer. Now, process specifics may vary depending on certain factors such as material type and part geometry. However, the information provided here in this lesson will provide a basic understanding of thermoforming that's needed for subsequent lessons. All right, so now that we have a basic understanding of thermoforming and how it compares to other plastic processing technologies, let's move on to our next lesson, packaging polymers, where we learn about different polymers and how they're used in the packaging industry.